Let's talk about proof by contraposition now. If you remember from the previous videos, we know that with a proof by contradiction, we are looking to assume that the then part is false and show that the if part is false. Another way of looking at it, of course, is, well, the word contraposition is there for a good reason, because we can write the contrapositive of the statement and then just prove that directly. So the contrapositive of if n squared is even, then n is even, is if n is not even, and since we're in the integers, if you're not even, you're odd. If n is odd, then, well, n squared is not even. Again, we're in the integers, so n squared is odd. And it ends up being the same thing. Assuming q false, that's exactly what we're doing if we do a direct proof of the contrapositive. And we need to show that p is false. So we need to show that the then part of the contrapositive is true. Remember, this is logically equivalent to a direct statement. In fact, with this one, you could try to do this directly, assume that n squared is even, try and show n is even. That's actually a very, very tough way of going. It might be instructive to try and write that down yourself and see that you can't get anywhere in particular. There's no nice way of going from n squared to n. You could say, well, I'll take the square root. And then you're taking the square root of something that really doesn't have a nice square root. So it becomes quite difficult. So a lot of times, if you find the direct proof difficult, try the contrapositive. That might be a good way of going. So here, if we prove that if n is odd, then n squared is odd, because this, the contrapositive statement, is logically equivalent to the original conditional, if n squared is even, then n is even. If we prove the contrapositive, we prove the original statement. And this should look familiar to you. From the last video, we proved this. So this was proved in the previous video, which is excellent. So now we know, and we have shown, that if n squared is even, then n is even. We proved the contrapositive again in a previous video, so we get the original statement here. We know if we have n squared is even, we know n itself is even. Let's do a couple more examples. Let's try this one. We have some number that is a rational number. Okay, so that's just set. And we want to show that if s is irrational, then r times s is irrational. So let's set this up. We just have r just as a number there. It's not part of our if-then statement. So we can first just say let r be a rational number. So r is a over b for some a and b that are integers, and b, of course, isn't 0. Okay. So my suggestion for you guys is to pause the video now, write this out as its contrapositive, and then try and prove the contrapositive. So pause the video now and try that yourselves. Okay, now that we're back, the contrapositive, well, we're going to assume that the then part is false, implies the if part is false from the original conditional sentence. So let's go ahead. So, if r times s is not an element of the rational, so that means it is an element of the rationals, then s is not an element of the rationals, so is an element of the rationals. So this is what we want to prove. This is the contrapositive. We are going to assume that r times s is an element of the rationals, and we need to show that s is an element of the rationals. Equivalently, we wouldn't have to write down the contrapositive statement. We could just assume that the then part is false, assume that r times s is a rational, that's the exact same thing, and show that the if part must be false, so s is a rational. Exact same idea. So let's do our proof. And it's a good idea here, when you're doing a proof by contradiction, let people know so they can follow along. Or sorry, by contraposition, not by contradiction, by contraposition. We'll do contradiction next. Okay, proof by contraposition. So, assume that r times s is rational. So what does that mean? That means that whatever number rs is, I'm treating that as just one number, that can be written as a fraction. We've already used a over b to talk about r. So we'll talk about r times s as c over d, again, for some integers c and d, and we can't divide by 0. So, I want a d, not a b. D is, of course, non-zero. We need to show that s is some integer over some non-zero integer. Again, this is informal notation, but it's a good training wheel to have when you're first learning how to do proofs. Okay. So let's consider r times s, and we know that equals c over d. And we also know that r is a over b. So we have a over b times s equals c over d. And of course, all we need to do is multiply by the reciprocal of a over b, so times b over a on both sides. And we get that s equals, well, we get b times c over a times d. B times c is an integer, a times d is an integer. So I'm going to ask you, is this correct? So have we shown that s is indeed a rational number? Pause the video and think about that. Maybe this is false somehow. Okay. Now the problem is, what if a was 0? Well, if a was 0, then we'd have 0 times d is 0, and we'd be dividing by 0. And that's no good. S wouldn't be a rational number, because a times d is not a non-zero integer. So in fact, this result isn't particularly true yet. So in math, a lot of times you're working on a result, and you find that there is something that you overlooked when you were doing the setup for the problem. So you're going to have to go back and add a condition to what you've been working on. So our problem here is that we don't want a to be 0. So what does that mean? We don't want a to be 0. So up here, we don't want r to be any old rational number. We can't have r be 0. We can't have the the numerator here be 0. So let's modify our statement. So we're going to say r is a rational number and r is non-zero. So that means that a is non-zero and b is non-zero. So let me add this in blue, just so you know what we're updating here. So we have a, b are integers, and a and b are not 0. So adding that, now we have a good argument. So now we can write, since BC and AD are both integers, so rather than saying BC is an integer and AD is an integer, you can just put a comma between them, and it's clear that you're talking about BC and AD since they're both integers. And A and D are not equal to 0 by assumption. We have that we just wrote s as an integer over a non-zero integer. So let's scroll just a tiny bit and say, thus, s is indeed a rational number, and we're done our proof. Okay, let's scroll down here and do the next example. All right, so again, maybe I'll let you try this in its entirety. So pause the video and try this. See if you can get this one to work. Remember, you want to either write it as the contrapositive and then do a direct proof, or just assume the then part is false, show the if part is false. Okay, now that we're back, I'm just going to do it by assuming the then part is false and showing the if part is false. So we'll do a proof, and we'll tell people it's by contraposition. So let's assume that x is not odd, so it's even, because we're in the integers here. So what does that mean? That means that x can be written as 2 times some other integer. And I introduced this integer k. Let me tell people that it is indeed an integer. And again, we want to show that this expression, x squared minus 6x plus 5 is not even. We want to show that the if part is false. So we want to show that this is indeed odd. So what does that mean? That means that x squared minus 6x plus 5 can be written as 2 times some integer plus 1. Okay, so let's consider that expression, x squared minus 6x plus 5. Let's use our assumption here. We know that x... Oh, I made a small mistake here. I said this is an element of 2k. That doesn't mean anything. X equals 2k. So here we are. Let's do this. X equals 2k. So let's put that in. 2k squared, that's x squared minus 6x, which equals 2k, plus 5. And you could start to see here things. Look at this. We're definitely going to have a factor of 2 here. We're definitely going to have a factor of 2 here. This is odd, so we can take out a 1, and we'll have something that we can factor out a 2. So let's do all of that. This becomes 4k squared minus 12k plus 4 plus 1. We have our plus 1. Look, there it is. And each term here has a factor of 2. Let's factor it out. We get 2 times 2k squared minus 6k plus 2 plus 1. And again, we have a bunch of integers added, subtracted, and multiplied together. So this is still an integer. So we can say since 2k squared minus 6k plus 2 is indeed an integer, we know our original expression, x squared minus 6x plus 5, is odd. And in fact, that completes our proof. So remember, with contraposition, the whole idea is you assume the then part is false. You show that it must be the case that the if part is also false. We've done that, thus the original statement here, this conditional statement, is indeed proven to be true.